All right. Hello everyone. Welcome to the second lecture of this course. I hope you managed to go through the homework that Sumudu has prepared for you regarding basics of game theory and how do you know, write a game in strategic form, how do you find equilibria in a game, and so on and so forth. So now we will be moving actually to the second part, which is going to be about reinforcement learning, and then we will see the link with the notion of games, which will clarify why we actually talked about the notion of equilibria. All right. So the recap so far, just in a nutshell, you should be now familiar with what is a strategic game, right? How do you formalize it? How do you write it in a strategic form? I think this was done also in the homework. What is the definition of a pure strategy, right, in a game versus a mixed strategy? I think this is now very clear, right? For pure strategy, this is essentially where the player or the agent selects an action with probability 1, whereas in a mixed strategy, well, he basically randomizes over the action space that he has, and this is why it's called mixed strategy. Okay. We also saw that, of course, John Nash gave us the definition of the existence of a mixed strategy, which is not always the case for pure strategies, right? So essentially, we also see that in practice, using mixed strategy is much better in terms of performance. And then you now should be familiar with the definition of a Nash equilibrium, right, in a game. And we will see also in this lecture different concepts of equilibria which go beyond Nash. Yeah. Then you saw how to calculate or find this Nash equilibria in very toy examples, but also in the homework, I think you went through a list of problems. Essentially, I mean, it's very easy to calculate. There's no secret behind it. Once you write down the the definition of Nash equilibrium and iteratively find it using best response, essentially, right? Then we saw last time actually that of course with Nash equilibrium we talk about optimality versus satisfaction or stability. Essentially, sometimes you are not interested in being optimal in terms of equilibrium, but you want to guarantee certain say target rate. If you take a wireless communication setting, and there we talk about notion of satisfaction games as opposed to a general game. Okay. All right. So let us get started with the part 2, right, which is about reinforcement learning. So just to remind what is the goal in RL. So here the goal is, as it's written here, is to design very fast, convergent, and efficient learning algorithms with a number of assumptions. So first, the information is minimal in terms of an agent not being able to observe the information coming from other agents. So essentially, agents do not observe what type of actions other agents take, what is the strategies, and so on and so forth. Right? The signaling is also minimal in the sense of communicating among agents. We will see that actually we do not communicate in this type of learning settings, right? But of course, there is an implicit coordination that we will delve into. Feedback is very important in learning. I mean, this is very clear, right? You take an action, you observe a reward, and then you kind of iteratively select another action in the next iteration, and so on and so forth until you reach an equilibria. Memory, we will see what we mean here by memory, but essentially this is meaning that you store the mapping between, say, your states and actions, right? Sometimes it is good to have the notion of memory, but also sometimes it becomes an issue if you are limited in terms of memory, if you think of a resource constraint device, for instance, right? We seek also, of course, a low computational complexity algorithm, right? And maybe more importantly, we are dealing with notion of uncertainty. So uncertainty is all over the place in terms of the uncertainty about other agents, strategies, observations, right? And this is why we talk about notion of robust games, but we will actually formalize this in a more principled manner. And then of course one of the goals is of course we will see what we mean by learning. I mean, what are we actually learning? Are we learning the reward of a given action of a given agent? Are we learning the action? What exactly are we learning? And I would say how to learn these payoff functions or utility functions, right? Because one of the main issue will be that for every given agent, he will be he will be tasked with learning actually his own payoff, which depends on other agents due to the interactions, right? Remember, we are in a kind of interaction game here where any action taken by a given agent will be perceived by other agents because they are mutually coupled, right? And then we want to learn optimal strategies, right? This is one of the goals of reinforcement learning. And we want to learn the law of the environment by interacting essentially. All right. So what is actually the definition of strategic learning here? Just for sake of definition here. So the term strategic learning stands for how players learn from other agents, right? And their complex strategies and beliefs. And we'll see what we mean by beliefs here. A strategic learning consists of acting in an environment, so either optimally or in a satisfactory criterion. As I said before, it could be following a Nash or following, for example, satisfaction equilibrium, where the outcome of the game actually are interdependent, obviously, and happen in a dynamic manner. This is what we call it interactive. Okay? So as we said before, learning is used in a variety of disciplines. So machine learning, obviously, but robotics, distributed control, distributed optimization, economics, biology, game theory, and obviously networking and communication. I mean, there is a lot of work now in this branch of learning in wireless communication. All right, so let us now proceed with the definition, or let us understand what we mean by partially versus fully distributed learning. So in the partially distributed learning setting here, we want to learn optimal strategies based on observations of the past actions of other agents. Okay, so you have an agent, right? Of course, he can observe his own payoff because that depends on the action he takes, but also he can observe the actions of other agents, but previous ones. Okay, so kind of historical information that the agent gets access to. Okay, so under this definition, we have a number of learning techniques. So one of them is called fictitious play and variant. Another one is called cause to learn. There's also learning conjectural variation equilibrium, and also Nash bargaining solutions fall under this category, right? So contrast this now with the notion of fully distributed learning. Okay, so here, unlike the first learning scenario, the agent want to learn the optimal strategy based only on the observation of their own utility. In other words, the agent only gets access to local observation. Say, for example, this is a kind of reward he gets when he plays a given action, right? So it could be a vector, could be a scalar, could be anything you want, but does not observe what other agents have played currently as well as in the past. Okay, so this is basically the only difference, right? Which comes down again to the notion of information. What type of information the agent has, right? This will basically put it either in the first category of partially distributed learning or in the second one where we actually know nothing about other agents. Okay, so under here you have under this category, you have for reinforcement learning, which is the branch of reinforcement learning we are interested in. Regret-based learning, which is a very effective, actually, and technique in reinforcement learning. And we will contrast it with classical reinforcement learning. And then you also have other kind of techniques such as trial and errors and others. Okay, so just keep in mind for now that the notion of information is very important, because that puts you already, brings in the question of which algorithm am I going to use now. All right. Now for the overall picture in reinforcement learning. So here what you have, is very, very, very simple. You have a user, say a cognitive user or intelligent user. This could be an agent, okay? And this agent actually is interacting with nature. So nature here could be the environment, right? Could be the other agents in the environment, right? So the agent will model this environment as with a given distribution, because he doesn't have any information about it. Okay, but obviously this environment will play a role in terms of interference, for instance, in the case of wireless communication. Okay. So this user has to choose a given action or strategy, right? And we essentially receive the payoff or utility, right? R tilde WA, which is the instantaneous payoff that the agent gets, which is again a function of the uncertainty coming from the environment, right? And its own action, right? So when we write this down, essentially it comes down to maximizing the expectation over this reward, right? Because here you just take the expectation, you average over the actions of the player as well as the uncertainty. Again, that could be anything from the interference distribution, could be the location information distribution, could be anything else that the agent does not observe. Okay. Now this utility here, or payoff R tilde WA, is essentially unknown to the player, because this utility will actually depend not only on the agent observation, but also other agents. So here you'll see actually an interaction between all the agents, right? W, we said already, is a random variable, right, which is unknown to the agent. So its law or dynamics are unknown, right? And the goal here is to design very fast, efficient, and convergent learning algorithms such that the agent can learn, one, its own payoff function, right? Two, what is the optimal strategy that the agent needs to take at every iteration. Okay. Of course, this is not a one-shot game. This is a game that happens over, say, a time duration, and this is why we talk about long-run interaction. Okay, so it's a very simple setting. Okay, all right. So previous lecture we talked about the notion of equilibria, right? We talked about, okay, if you have a game and I give you these are the payoffs, for instance, you can characterize the equilibrium. You can say, okay, this is a Nash equilibrium, and so on. So you can say this is an efficient equilibrium. But we didn't talk about how do you approach, how do you converge to this equilibrium, right? So we didn't talk about the algorithmic part, which is essentially bringing us to this lecture. So learning, of course, we saw that it's a process through which players reach a desired point, for instance, a Nash equilibrium, right? And since we are in a multi-agent setting, right, we know that actually game theory is only useful to characterize, again, the existence, uniqueness, efficiency of the Nash equilibrium. But what we are interested in now is the algorithmic part, okay? So we will now look at another family of equilibrium called a correlated equilibrium, which we will try to first define, okay, contrast it with Nash equilibrium that we saw in the previous lecture, and understand the difference. So here we need to really to pay attention, because this is very important for what will come next in terms of applications and so on and so forth. And it will now expand our toolbox in terms of equilibrium. All right. So correlated equilibria was actually introduced by Robert Ullmann in the 70s, for which he got the Nobel Prize. Essentially, he wanted to generalize the notion of Nash equilibrium, right? So now, if you remember from last lecture, one of the assumptions when you have a Nash equilibrium, when you look at the definition, you essentially see that when you write down the joint probability distribution over the actions of all the agents, it is actually factorized in terms of independent distributions, okay, per agent, right? Now, this may not be actually useful in the sense that it does not capture the mutual interactions or the correlations between the agents. And we know very well actually that in practice you have always correlations in terms of what agents observe, right? In terms of the signaling they get. So essentially we need to now look more into correlations. And this is actually why this concept of equilibrium is very interesting, because now we assume that there is a coordinator, right, or arbitrator, which is basically sending private or public signals, okay, to these players, essentially helping them via this implicit coordination signal to better achieve better payoffs, as opposed to if they were acting completely independently, right? This arbitrator or coordinator doesn't have to be smart entity in terms of computing the Nash equilibrium or correlated equilibrium, because it's not doing it here. It's just used as a signaling point. And we will see as an application actually later on that this entity does not have to be a physical entity, as of a base station or a server. It can be done in a completely distributed manner. Okay. So what's an arbitrator? Well, it could be, yeah, a base station sending signals, or maybe just a virtual entity, right? And why is this relevant? Obviously, in a wireless setting, this is going to be very important, as we will see later on in some of the examples. But I think you get the idea here, right? We need to have this signal, which would be sent by any entity in the network, which helps the agents better self-organize. Okay. And what is very interesting, because Robert Aumann actually extended the notion of equilibria, of Nash equilibrium towards CE. So correlated equilibrium actually includes Nash, right? And is more efficient. Okay. So loosely, if you didn't understand anything so far, loosely, the correlated equilibrium will generate random joint probabilities rather than independent individual mixed strategies as done by Nash equilibrium. Okay, so just keep this in mind. All right. Now let's take a look at the definition now of correlated equilibrium. But just if you just jump here to look at first the definition of Nash. If you remember from last week, we saw that actually the definition of the Nash equilibrium is very, very easy, in the sense that if Sj corresponds to the, or sorry, rather Sk corresponds to the Nash equilibrium, this means that the utility that the player K will get at the Nash equilibrium will always be larger than if it deviates essentially from this equilibrium, right? So for any other deviations, the agent will get a lower payoff, and therefore he would rather stick to that equilibrium. I mean, essentially, this is what it meant. But here, pay attention to this distribution pi j equals 1 to k pi j sj. We write it this way because essentially we are making the assumptions that the distributions are completely independent. Okay, so the agent is actually completely decoupled from the other agents. So what the Robert Aumann did, in fact, he said, no, this is not a good idea. And now we need actually to go back and try to now, instead of writing this as a product of distributions, we need to now write it as a joint distribution. Essentially, this is what he did, right? So let's take a look at the definition. So consider the game G here. This is the strategic form, so I hope you are now familiar with the strategic form. This is the set of player K. This is a set of strategies Sk, right? This is a set of utilities or payoff for every player K. Let pi be the vector, so pi S1 until pi S cardinality of S. This is basically the vector of strategies, right? So pi is a probability distribution over the set of joint actions S, right? and denote by pi Sn the probability that of an agent observing an action profile Sn, basically. Okay, so the definition says that the probability distribution pi is a correlated equilibrium if for all players k and for all strategies S prime k, we get that the expected utility of the player k, okay, at the equilibrium will be always larger than if it deviates from this strategy, basically. So essentially the same definition as in Nash. The only difference is now we do not make the assumption of independent probability distribution here for the actions, but we now take into account the joint distribution. All right, so I hope this is very clear. Now, in practice, what does it mean? It essentially means that agents will choose whether to follow the recommendation given by this public, say, signal, right, after it receives it. So first, it receives this implicit signal, say from the base station, if we're talking about users as agents, right? So the base station will now act as a coordinator, right, issuing signals, right, to help the users kind of optimize their power, for instance, accordingly, right? So this definition here says that the agents first receive the signal from the base station and then decide whether to follow it or not. Okay. All right. So again, very simple idea here. Essentially, we'll give him the Nobel Prize, but I mean, yeah, we will see. If you go back to the definition now of coarse correlated equilibrium, if you have, let's say, k agents, well, you need to write down all these inequalities for all the agents and recursively calculate the corresponding utilities, obviously, but also the equilibrium that you will get. Okay, and this is why you get actually this set of inequalities giving rise to this blue curve here corresponding to the achievable region in the case of coarse correlated equilibrium. Okay, so the take-home message here is essentially that the coarse correlated equilibrium provides us a much larger set of possibilities as compared to the correlated equilibria and the Nash equilibria. It turns out actually sometimes the Nash of equilibria actually matches the set of correlated equilibria, but this is not always the case. This is just a kind of an example where they basically collapse, but this is not always the case. All right, very good. So let's go back to now our learning process, right? So essentially, we know by now that learning is essentially an iterative process which happens over time, right? Where players take actions at every time slot, and every learning algorithm will always have three key ingredients. So first, the agent needs to observe the environment at a given time t, right? Which will give it an idea of how well the player has actually played in the previous iteration. Then, based on the current observation, the agent will take a strategy pkn, okay, if n corresponds here to the time, or k is the player index. Then it will select an action akn according to strategy pkn. So remember before we said that the action is not always synonymous with strategy. Well, here's an example, right? So there's a mapping between actions and strategy here. So here, based on the strategy of a given player, you take a corresponding action, right? But they are not always identical. And finally, learning ends conversion when the strategy vector ends up converging to an equilibrium after a finite number of iterations. I mean, this is what we mean here by learning, right? I mean, very simple. Okay, without any surprise for now. All right. So now let us go through a family of very popular learning algorithms, which essentially will now recapture notion of Nash equilibrium, correlated equilibrium, and cross-correlated equilibrium. So now we will see the algorithm that allows us to converge those points. All right. So one of the simplest form of learning is what we call best response dynamics. And essentially, this is exactly the algorithm that we used in the beginning when we were playing with those toy scenarios, when we were looking for the how to find the Nash equilibrium, say in a 2x2 matrix game. We actually use this notion of best response dynamics. Okay, so we use it to find the pure strategy Nash, right? And we can even use it to find a mixed strategy Nash. This is not an issue. Now, to use this algorithm, it could be used now in parallel, right? Say agents use it at the same time, or it can be sequential, where every player will observe the actions of other players. So key point here is actually you can observe what other agents are taking as an action. And remember here, we said before that we need to understand now what type of information we have, right? So here it's an assumption that the player will observe actually the actions of other players. And subsequently, the player will choose the action AKN, which will optimize its own utility given other players' actions, which are observed, right? Now contrast that with the parallel case, where in the parallel case, essentially all the players optimize their given the actions at time n minus 1. I mean, this is not very important to remember here. But what's important here is that the player is observing all the other actions from all the other players, which is not practical, but just for the sake of explanation, I think it's very important because it will bring us to the other more complicated case. All right. A second famous algorithm is called fictitious play, and which was proposed back in '51 by Dr. Brown. So fictitious play is actually seeking now mixed strategies, right? And it's one of the actually simplest algorithms for finding them. What do we have? So here, every player will have this notion of belief, where it believes what other players play following a fixed probability distribution. So you have k agents, and every agent now will make this assumption that, or belief, that all the other players, okay, are following a fixed probability distribution. Again, this is not very practical, but actually it could happen in certain cases to, for example, reduce the complexity of the learning algorithm. Okay. So at each iteration n, every player will observe the past actions of all other players. Okay, remember, this is actually how every agent now will build a belief on what type of strategies all the other agents are using. Okay, so what do we mean by this belief? For simply, this belief corresponds to the empirical frequency of dates, essentially a counting measure of how many times a given action has been used by those agents. Okay, so it's a counting measure, right? And then you calculate essentially your belief based on that, right? So using this belief, every player will now choose the action that maximizes its expected utility with respect to the beliefs of all the other players. So I think it's a very, very simple rule here for learning, right? Now, it's important to remember that here every agent will assume that all the players are, again, following a stationary distribution, okay? This is a key here, the key assumption. And again, this is the same thing as before. The fictitious play here can be either sequential or parallel. All right. So mathematically, how do we write this down? So first of all, you calculate, so what's the belief here? So the empirical frequency f bar j t s g is nothing but actually, so if we take I mean, this is the player j here, time t, this is a strategy sj, will be basically calculated as follows. So we just take, so anytime the player j at time t prime takes strategy sj, okay, then you calculate basically essentially how many times this has been done, and you just take basically the moving average here, right? That allows you to calculate this empirical frequency. Okay, so up until time t, how many times strategy sj has been played, all right? Now, because we want to now implement this algorithm now kind of recursively or iteratively, we can write this down. So f bar s g at time t plus 1 is actually equals to f bar jt, right, plus something. And this something actually corresponds to, yeah, epsilon here is a kind of a learning rate. And then this is essentially saying that, okay, one, when the player is actually taking strategy as j, right, minus f bar the empirical frequency at time t. All right. So I mean, it's very easy. You can actually write. I mean, write down the proof. I mean, usually I would give you 5 minutes to write this down. But essentially, yeah, you start from this, right? You start, okay, at t plus 1. So if I replace t plus 1, so I get f bar jt plus 1 of sj equals 1 over t plus 1, the sum over 1 until t plus 1, right? This indicator function here. And then you can write down this t plus 1 multiplied by f bar, right? I mean, you get the idea here. And essentially, the learning rate will be very easy to find here, which corresponds to 1 over t plus 1, okay? So this is how we write down iteratively the calculation for the empirical frequency for strategy SJ. So this has to be done now for all strategies. Remember, every player has SJ strategies. So, but it's very easy. You can get the idea. All right, and then once we have this empirical frequency, well, the agent now has basically to take the argmax. So he wants to maximize its utility. Remember, right? So essentially, take into account now the empirical frequency of all the other agents here. Minus j correspond to all the other agents except agent j, right? And then he takes this into account using these easy calculations, right, we showed before. And yeah, and then basically, yeah, this is if the agent itself takes the action as j, then he just maximizes and finds the the action actually that maximizes this utility. Very simple rule, in fact, okay, very simple rule. Okay, and this fictitious display has been used in several applications, even in wireless communications, such as power allocation. And all right. So now, how useful is this result, right? So now consider a sequence of measurements of a random process, right? And we want to estimate, for instance, the mean or the variance of, say, the outage or the outage probability, right? This recursive equation helps compute the mean in a recursive manner with only one-step memory. So this is the advantage here when I was talking before, with the notion of information, but also memory, right? Because now instead of keeping all the sequence of all the actions of all the players, right? In memory, of course, if you are limited in memory, you cannot do that. Therefore, you'd rather just keep in memory a scalar value which corresponds to, okay, a number of to represent basically how many times this action has been adopted by other players. Okay. So again, I mean, this is just a recap of the previous slide. Essentially, how that fictitious play is a very simple learning rule, yet has advantages in terms of memory, right? Which, for instance, the other algorithms do not have, right? So if you're looking for a very low complexity algorithm, fictitious play is a very competitive one, right? Now, of course, we here in the definition of fictitious play that we use, we made an assumption that here we are in a pure strategy case, right? So here the indicator function indicates again that the action that the player J will take, okay, is equal to the strategy Sj, but this is not a limitation, right? So here we could replace this basically by a probability distribution function, right? As we did in the mixed strategy case. And this is why there are other variants of a fictitious play called smoothed fictitious play, which actually builds a probability distribution now, right, for the mapping from action to strategies, right? So now we will see in the future slides that what kind of distribution we need to put here, right, when we are in the kind of mixed strategy case. Okay. All right. And now, yeah, I mean, again, this idea now of calculating these average quantities, of course, can be applied to calculate any belief. So the belief before was about, for instance, how many times this strategy has been used. But of course, you can use also this not only for the average frequency, but also, you know, for the average payoff. I mean, essentially writing down iteratively, you know, this was as we did before, right? Because we were interested in calculating the average frequency for calculating the frequency of using action SJ, right? But you could do it also for the payoffs, right? And essentially, you can show that you can write down. So this is the payoff at time t+1 equals the payoff at time t plus a learning rate. Okay, and this is the, for example, the immediate reward that the player J will get minus the previous one at iteration t. Okay, so this is a kind of the way we write down this average payoff quantity in a more iterative manner. Okay, because at the end of the day, we need to come up with an algorithm, right, where at every time t, the agent needs to decide, you know, how to update its strategy, and most of the time that will be done based on the immediate reward that it gets, as well as a previous reward that it accumulated up to time t. All right. Then here finally, just to say that I mean this step size or learning rate that we used before, so this is a very important, obviously, for the convergence of the learning algorithm. So it could be, of course, fixed step size, but it could also be proportional, right? Proportional to what? Well, it could be proportional to, for instance, the payoff that the agent get, for example, right? It could be following different rules. We will see actually later on what kind of step sizes are more suited when we want to apply these techniques in a wireless setting. All right. Okay, good. So now we move on to the third family of algorithms. So again, we look at the best response dynamics as the first one. All right. Then we move to the fictitious play, and the third one will be about regret matching. So unlike fictitious play and best response dynamics, which are based on maximizing your utility, right? Here, regret matching, as the name suggests, will be based on the notion of regret, right? So now the players or agents will minimize the regret of not playing a given action. Okay, so now mathematically what it means, if I want to calculate the regret for a given action here, A, right, for player K at time n, this is equal to the sum from t equal 1 to n minus 1 of the utility that the player K will get when it always selects this action K, right? This is the other agent's actions, minus the utility that it gets when it takes a general AK. So here it randomizes. Remember, A is a set of is an action of the player. So at every time T, he has a decision to make, either to always use the action AK or randomize. Okay, so essentially the difference here is essentially telling us what is the regret that the player will get if he, you know, always at every time T plays the same action, right? Versus the kind of if I randomize it every time T. Okay. And this is essentially what we mean by regret here, right? So now instead of maximizing the utility as we did before, the agent wants to minimize this quantity, right? Because now if this quantity is larger than 0, right, it means that the agent actually should stick to this action K, right? This action AK, right? Right? Whereas if it's smaller than 0, well, actually no, it's not a good idea, and therefore he needs to now randomize his strategy. Okay. Okay. Very good. So now the actions that will be taken by the agent will be according to the probability distribution found by normalizing this regret. So what happens is that now, remember, this is a regret for action AK, so we will need to have the same equation for all the actions, right? And then basically the action that the agent will take is to calculate the probability distribution, which is just to normalize this regret vector. Okay. All right. Now, this is the vector. Yeah? So you have to calculate this, which is basically the vector of all the actions, right? AK1 until nk. So here the agent has nk actions, right? Very good. So keep this in mind because we will come back to it later. So what do we have, right? So in reinforcement learning, players will follow a certain behavioral law. We will use this terminology very, very much because this is one of the kind of important aspect of the learning. Okay. So the action set is assumed to be finite, right? This is one of the assumptions in this type of learning approaches. The utility is bounded, and every player will periodically observe its own achieved utility. Okay. And because this is very practical too. I mean, if this is a user transmitting, I mean, the user will always see locally what type of reward he gets, right? And then the idea behind reinforcement learning is that actions leading to higher utility observations at time t or at time n or stage n here are going to be granted with higher probabilities at the subsequent game stage n+1 and vice versa. Okay, so this is very logical. The action that gives you higher reward, right, will be chosen more often than the actions that lead to lower reward. All right. And what we will be interested in is estimating the utility of every agent, right, and the action that it will choose based on local observation. Okay, so this is exactly how the learning will happen. Okay, we will need always to estimate two quantities: the utility that the player gets, okay, at time t, and the action that it takes. All right, and here, of course, the action will be mapped to the strategy that it will adopt. Very good. So here just some observations to basically stress again the notion of information. So how much information is needed to learn. So we saw that actually for best response dynamics, fictitious play, and regret matching, the players must observe all the actions of all the other players. So this is of course not practical with large overhead, right? Especially in a wireless network. So we will see how to overcome this limitation. Now, this is where actually reinforcement learning has an advantage, right? So we will see that actually we only need an observation or estimation or measurement of the utility to carry out the learning. We do not need to observe what the other agents are actually taking, okay? And best response dynamics, fictitious play, we need to solve an optimization problem. So of course they're computational more demanding. We saw that actually fictitious plays maybe has an advantage in terms of memory requirement, but still you need to calculate this or solve this optimization at every time t. It can be also of course computational demanding. All right. Yeah, so now of course if we are talking about convergence issues, because now of course the learning is one part, but we are often interested in whether this algorithm converges and not, right? And whether if it converges, does it converge to the set of equilibria we discussed before, namely Nash, correlated equilibrium, coarse correlated equilibrium. Do we have one or we have many equilibria, right? So essentially in general we only have sufficient conditions which are available. In other words, the convergence is not always guaranteed, except if we fall in a certain category of games. These games are called dominant solvable games. Potential games are very popular in wireless communication too, and zero-sum games. Once your game is cast as this type of games, we immediately can talk about convergence. Okay. In addition, conversion speed depends typically on the amount of information that is available to the agent, right? So for instance, fictitious play and regret matching are faster than reinforcement learning. Faster because we made the strong assumption that the agents observe all the actions, right, of all the other players. Obviously, the conversion is much faster, right? But in practice, this is not the case. So I said that potential games are very popular in wireless communication. So just to give a definition of what we mean by exact potential game. So let's take the strategic form game that we introduced before, right? So again, K the set of players, PK here is the set of, say, power allocation if you want here, PK, and this is the utility of the player K. We said that this game is an exact potential game if there exists a function phi p, right, for all p here, such that for all players K and for all actions P prime K, the following holds. So this says actually that the difference between the utility that the player K sees, PK and P prime K, will be equal to the same difference if we take this function phi here of PK minus P prime K, okay? The advantage of this definition is actually that you can map all the players' utilities, right, to this function here. So this function actually is actually capturing all the players' finite difference between if you choose action PK and if you take action P prime K. Okay, this is why we actually interested in generally maximizing the utility phi instead of the utility UK. Okay. Now the question, of course, is how do you find this function phi k here? And there are many other. I mean, there are many ways to do that. And again, this is a very interesting idea. I mean, I will share with you some reference later on. Yeah, if you're interested, for instance, how to apply the potential games in notion in the context of power allocation. Okay. So again, just to conclude here, potential games, which is one class of games, of course, there are many others. Here, the advantage is we can guarantee the existence of a pure Nash equilibrium. Good. Now, yet another algorithm in reinforcement learning called Bush-Mosteller, which was actually proposed back in 53. So you can see that all these algorithms, in fact, date back to the 50s, right? So yeah, long time ago. So what do we have here, right? So again, let's pay attention to the information part. So here we said that every player J is assumed to know its action set. This is fine for now. And the maximum absolute difference between the payoff, okay, she may receive and the aspiration threshold, or call it a threshold, okay? This is essentially what the agent knows, okay? And moreover, the players do not use any information regarding the other players. So the only thing the agent knows, again, is its action set, okay, and the maximum difference, okay, between the payoff it gets and the kind of the target payoff that it wants, okay. So in terms of computational capabilities and memory, here the players know their own mixed strategies at every time t. This is not an issue, okay. So now how does this work, right? So here, if you want to calculate the strategy, it will be a function of RJT. Okay, this is kind of the reward that the kind of the player gets. Okay, that he observes basically at every time t, minus MJ. So MJ here is actually the aspiration level. So call it the threshold rate, right, or a threshold reward. Okay, and then you normalize it here by the supremum, because remember we're interested in the maximum absolute difference, right? And this gives you this SJT, which could be seen as the kind of the strategy, okay? And then you actually do what we did before, right? We want to write down iteratively the update for the strategy, okay? Which here corresponds to xjaag, okay? At time t plus 1, which is gonna be equals to xj ajt plus this learning rate lambda j multiplied by this sjt, okay, multiply 1 minus xjt, okay. If the sjt is larger than 0, remember, this is what I'm interested in here. So if the agent finds out after calculating this expression here that this is larger than 0, okay, therefore I will update my strategy according to this equation, right? Otherwise, I will just basically use the same strategy I used in the previous time t. Okay, this is essentially how you update. I mean, the update rule for the Bush-Mosteller algorithm. Okay, you just calculate this quantity here, SG, and then you use it actually to update your strategies. Very, very, very simple. Of course, I mean, it has some issues here. Essentially, that this is a pure strategy case, but still, I mean, you can apply in certain settings. Okay. One limitation here, perhaps, is that this RJT here also has to be estimated, right? So here I'm talking about updating the strategy, but you could also estimate RJ because, of course, this is not obviously given to the agent, right? But again, this is an information assumption that was made. All right. Now we want to also see how to learn this correlated equilibrium. So how do we do that, right? So here, I mean, this is the same notation as previously introduced, right? So I'm interested in the regret of player J, right? So here, how do you write down this regret? Just for a reminder, this is the difference between the utility that the agent gets when it always chooses strategy SJ, right? Minus RJA here, this is to say this is when you randomize your strategy. Okay, so very simple. Okay. The difference between when I always choose this strategy minus when I randomize. And then this is a difference which gives rise to the notion of regret here. Okay. And now what you do, we said before that you normalize this, and then you can actually find what is the kind of the maximum regret, and this is what will drive the dynamics of your only updater strategy. Okay, this is essentially what is written here. Okay, this is the same thing, right? What's interesting is essentially that Hart and Mas-Collar back in 2000 have provided us with a nice result, convergence result, which say that if every agent plays according to this no regret dynamics here, right, then the empirical distribution of play, right, ft here, which will converge almost surely as t goes to infinity to the set of correlated equilibrium. Okay, so now if I take my strategic game, I don't maximize my utility, but I want to minimize my regret. So this is a no regret dynamic, right? I calculate this quantity here, which corresponds to the regret that you get for every per strategy, right? And then if I follow this kind of update strategy, then I'm guaranteed that I will converge to almost surely, right, to the set of equilibrium. So of correlated equilibrium, which could be, of course, more than one, right? This is the very nice actually result. If you are interested in proving convergence, okay? All right. Now remember, we went through a number of algorithms, right? So you need to keep in mind actually, right, what we looked at in terms of information assumption, right, for the agent. What does he observe? Does he observe the other agent's actions? And if so, is it the current observation, or does he have a kind of historical information or belief? And then does he assume that the other agents' beliefs are static or are changing, right? So Boltzmann Gibbs actually is one of the most powerful learning algorithms, and this is an approach that actually we used extensively in a number of works, actually well-cited works in the literature, and you will see actually why it's very important. So one key aspect is that every agent will need to estimate the payoff. We said before, we repeatedly said that we need to estimate. So what do we estimate? We estimate the payoff, right? And we need to make decisions based on this estimation, right? This is essentially what Boltzmann Gibbs learning will do. Because once I estimate my utility, and then I use that utility to update my strategy, this guarantees me that actually that I am not, communicating with other agents. I'm learning completely in a totally distributed manner, while achieving kind of a good outcome in terms of equilibrium. All right. Here basically says that the payoff of the chosen alternative are observed, and is used to update the strategy. So essentially here, what the agent will do will build a probability distribution over the set of actions that it may take, right? And then every time t, it will actually pick a strategy following this distribution. So now, if that action gives you a higher reward, then you will update it. Basically, say that this reward, this action, actually should be selected more often. But all the other alternative actions, okay, will still be useful at some point, because you will always maintain kind of a lower probability over those strategies that give you a lower payoff, because it turns out that actually, because of the dynamics in the learning, those actions that give you lower payoff may in the future be the one that give you a larger payoff. So this is why we need to play a trade-off here between the action that you take and give you good reward, and the actions that actually you take and do not give you a good reward. Okay, this is basically the same thing. And then of course the learning again is repeated over time, and gives rise to this stochastic learning process. Okay, all right. So what is this Boltzmann Gibbs distribution? I mean, we can spend an entire lecture on this this distribution, because actually it has a very nice historical kind of part to it. Essentially coming from statistical physics, and then it ended up even in information theory, and then later on in machine learning. But yeah, maybe for the sake of time we won't have to do that. But for those interested, yeah, there is a lot of literature on this aspect of Boltzmann distribution. So let's take a look at the definition of this distribution. So as you can see here, so the Boltzmann distribution is written down as follows. So beta here, which will be corresponding to the distribution, right? Let's stay still in the sake of the discussion in the game setting, right? So here you have again a game, right? And you have player J. This is strategy Sj. Okay, this is the reward that, or estimated reward, I should say, that the player J will see at time t, right? Will be equal to exponential 1 over epsilon j r hat jt sg divided by the sum of all the actions, essentially, or strategies. Okay, this is what gives rise to the distribution. So this, and what you should pay attention to for now, is that there are some parameters here. There's a parameter epsilon j here, which corresponds to what we call the temperature parameter, which will play a key role in the learning process. This is the parameter that actually will allow us to randomize our strategies, okay, over time. Okay, now if you plot this distribution, you will see actually how it evolves as you vary this temperature parameter here, epsilon j. So again, just keep this in mind, because we will come back to it. This is actually what we mean by a Boltzmann-Gibbs distribution. Okay. Yeah, and this of course will be the solution to most of the games that we'll be essentially looking at. All right. So this notion of Boltzmann distribution will be solution to this type of learning games. Okay, so here what do I have? This is called CODIPAS for Combined Fully Distributed Payoff and Strategy Reinforcement Learning. This is essentially, as I said before, one of the most powerful frameworks. So what do you have here? Okay, so maybe let's jump here first. Okay, so in the second part. Right? So here, what am I writing down? I'm writing down two coupled equations. So the first one is actually, this is how I write down the update of the strategy for player J at time t plus 1 when he chooses strategy Sj, right? Again, this is the same iterative formula we showed before, right? And that was the motivation why we started with that. Okay, so essentially it says that if the action taken by player J at time t equals Sj, then you will update your strategy accordingly, right? And then likewise for the reward or utility, you would write it down this way, and of course lambda and mu are learning rates. Okay, so far so good. Now, what we will be now doing instead is we will be replacing this indicator here by a probability distribution function, right? Which is exactly this beta here in the top equation here, right? So beta tilde j r j t is essentially what I presented to you just in the previous slide, which corresponds to which gives you the mapping between the utility, okay, and the strategy of the player J, okay. So what did we do? We essentially, I mean, this is just the same as it is. Just we wrote it, right? We take this indicator and replace it by this distribution, okay? And we will see why. Actually, we will see why we do that. Okay. First, intuitively, is essentially in learning you should not use kind of pure strategies in the sense that you will not need to always use mixed strategies, right? To randomize over the set of actions that you have. And if you do that, then the solution that you get will correspond to Boltzmann distribution. Okay, so if you don't remember anything from this course, remember that the Boltzmann distribution is a solution to this learning dynamics. Okay, where the assumptions here are actually very, I mean, we don't make any strong assumptions. We only need to know, we need to estimate the utility first. You can see here, I need to estimate for every action Sj the utility of the player that he gets, right? Once I get this utility here, I take it, so I take r hat, then I put it inside this update rule here, which is the Gibbs, the Boltzmann Gibbs, right? And then I update my strategy. Very, very simple. Now, of course, what we will see later is, because these are coupled stochastic equations, right? You have these learning rates here, mu and lambda. So this cannot be taken randomly, because essentially what we will need to ensure is that the estimation that we get for the utility has to be a very good estimate before I use it to update my my strategy profile. Okay. In other words, this learning rate has to be kind of very fast. Okay. So I can get this value here, plug it in my Boltzmann Gibbs distribution, and update my strategy X. All right. This is why it's called combining payoff and strategy learning. Okay. So R is the payoff or utility, and then the strategy is X. So I hope this is very clear, because this is a kind of the algorithm that we'll be using extensively. Okay. So as a summary, we looked at a number of learning algorithms, right? We looked at best response dynamics is here, fictitious play, then there was this smoothed fictitious play, then there was this regret matching, then there was this reinforcement learning, and then there is this just reinforcement learning. So let's look at the various assumptions that are related to all these algorithms. So one of them is first observation, right? What are the observations that you need when you use one of these algorithms? So in the case of best response dynamics, we said before, one of the strong limitations was that actually the agent has to observe the action of all the other players here, minus k, right? This is the same thing for fictitious play. This one is the same. Regret matching still the same, although it minimizes the regret as opposed to this tree here, which maximizes the utility. Now, in the case of reinforcement learning, we only need the UK tilde t here. This is just a local estimate of the utility. I don't need to know the actions of all the other players. So this is a very good news, right? And likewise for this variant of reinforcement learning. And we'll come back to it later. Now, in terms of closed form expression for the utility k, do I need it actually? Well, in all the cases, yes. Remember here, because I'm solving an optimization problem, so I need to know, I need to get a closed form expression of my utility. However, in the case of reinforcement learning, I don't need to, because essentially all I need is a scalar value of the estimate. I don't need to know the closed form expression. If I have it, that's good, but I don't need, right? Because the learning will be done based on this local estimate, okay? In terms of a complexity, well, I think, there are trade-offs here. So here, of course, you optimize. Here, you just need this algebraic operation here, because here you just have this kind of utility here at time t. Now, for the what type of equilibrium we converge to, I think now you understand that, best response dynamics converges to the Nash equilibrium. Fictitious play also converges to the Nash equilibrium. The smoothed fictitious play converges to a variant of Nash equilibrium called epsilon Nash equilibrium. Why it's called why it's called epsilon Nash equilibrium is because actually it converges to the neighborhood. So it approaches Nash equilibrium within a ball, say, of radius epsilon. Okay. Regret matching converges to the coarse correlated equilibrium, and then reinforcement learning. All these guys same. Epsilon Nash equilibrium. Okay. Then for the condition for convergence, as we saw before, it depends. I said before that if you are in the dominant solvable games, potential games, and other type of games, then you're guaranteed actually, right, to converge. So this applies to best response dynamics, fictitious play, smoothed fictitious play, yeah, regret matching here, right, and then other algorithm. Okay, so if you are in a potential game, it's very easy. You can immediately prove convergence. Okay. Then in terms of synchronization, because this is very important, especially for practical algorithms and settings, yeah, best response dynamics require that the agents are synchronized. Likewise for fictitious play, the variant of it, regret matching. However, the good news is for reinforcement learning and its variant, we don't need to ensure any synchronization among the players. Okay, as long as I get my local estimate of my utility, that's it. Okay. So it's a very powerful family of algorithms. Now for the environment, this is very important because remember now, of course, because again, we are talking about reinforcement learning, yet this is a kind of specific branch of reinforcement learning, okay? It is not the branch, this is not a family of algorithms such as Q-learning and deep RL, right? This is different in the sense that the environment is actually static, okay, or stationary, right? And we'll come back later when we talk about Q-learning. We will see what we mean by stationary dynamics and so on for the environment. Okay. So this is what I actually wanted to summarize here, right? Because it's very important to get the big picture here when we want to compare different algorithms in terms of information, complexity, in terms of memory, computational complexity, whether it converges or not. If it converges, can you prove it, right? Then you need to look at the nature of the game. Is it a potential game? First, you need to prove that it is a potential game. So this is a little bit the procedure that one should use when studying these kind of approaches. Okay, very good. Okay, so now let's look at kind of quickly of an application. In a wireless setting here, this is a application of reinforcement learning, comparing these different algorithms that we talked about now. In a 2x2 interference channel, this is a toy example still, but it kind of captures very well the nature of the algorithm that we get and how do we convert them. Okay, so we have a set of two transmit-receiver pairs, right, sharing S frequency band. This is also common in a spectrum sharing games, for example, right? We make the assumption that the channel gains are time invariant, right, for the sake of this example. Now, if the channel gain change over time, that will be actually already, it will put us in a different type of learning, which we will not adopt here. And the goal of this example is essentially to maximize, okay, the individual, okay, spectral efficiency. Okay, this is the goal of the game. Okay, so jumping directly to the result here, what we show is essentially what we're plotting here is on the y-axis. This is the average system spectral efficiency, okay, of the system, and in the x-axis we plot the signal to noise ratio, okay. from 0 to 20 dB for a number of algorithms. So you have the best response dynamics, you have the standard fictitious play, the smoothed fictitious play. Then there are many. There's a regret matching, and then there is this reinforcement learning one, cumulative one versus a just reinforcement learning. And then we also calculate the best Nash equilibrium, which corresponds to the case where you have multiple Nash equilibria, not only one, and you pick the one that maximizes the utility. All right. So what we can see here, and this is again, this is for two transmitters, two orthogonal channels. Okay. So what we can see here, first of all, is that, of course, as the signal to noise ratio increases, then, of course, the average, spectral efficiency increases. This is not a surprise here, but we can see actually that there's a difference between all these algorithms. So, for instance, if I take the best response dynamics in Dash red, you already see that actually it has lower performance compared to the others, right? So what we can see here is that the fictitious play, right, FP, and the smooth fictitious play, SFP, and regret matching, they always converge very close to the best Nash equilibrium, right? So the Nash equilibrium associated with the highest network spectral efficiency. However, of course, as we saw before, this performance comes at the price of assuming a lot of information, right, about the game, meaning that the agent observes the actions of all the other players. However, in the case of reinforcement learning and its variant, just RL, they are performing a little bit less, right? As you can see here, if you compare, for example, the best Nash here with the blue curves here, right? You see that they're performing slightly lower, right? But they are much less demanding in terms of information as we saw. So there's a trade-off here, right? If you have a lot of information, of course, you use those best response dynamics and fictitious play, you get a better performance. But if you are in a practical setting where you don't have much information and you want to learn only based on your own local estimate of your rate, for example, then you get lower performance. But again, you have used much less information. All right. So again, this was for two orthogonal channels, right? Now let's take a look at the case where now we want to plot the average system spectral efficiency versus the algorithmic iteration. So how many iterations it takes to convert, right? And again, we do it for all these algorithm we saw, right? So the black curve here, just focus on that. That's actually the best performing Nash. So it's ideally, that's where we want to converge over time, okay? So interestingly, what we see here, right, is that the regret matching and best response dynamics are the best performing and worst performing respectively. Why? Well, essentially because the best response dynamics, due to its nature of being myopic, meaning it optimizes the utility at every time t, right, as opposed to regret matching, which minimizes the regret, right? So minimizing the regret actually leverages the correlation among the strategies of the player. Remember the definition of correlated equilibria, right? Versus the definition of Nash equilibria, right? Now, by leveraging the correlation between this distribution, using, correlated signals, the regret matching gives you much better performance. But still here, of course, in this type of regret matching, we still make the assumption that the agent observes the actions of the other player. Okay. Now, what we see in the case of best response dynamics, it also showcases a kind of interesting phenomena of ping pong. Essentially, if you have two actions, now the agent, because he's myopic, he kind of, oscillates between these two strategies. Okay. Why? It's because actually here the assumption is that the players are simultaneously selecting the channel with the highest gain. Okay. So actually, what happens in practice is that this channel will turn out to be the best for both players, and therefore they will keep, changing, right? So this is the ping pong that we actually observe in this case. Okay. Now, if we move to the more interesting case, is that the one with 4 channels. Now we have 4 channels, 2 players. Okay. So what do we see now? Now we see actually that the best response dynamics will improve. Why? Because now remember, in the previous slide we had only two channels, so they kept ping-ponging, right, oscillating between these two actions. Now with four channels, well, of course, the impact of oscillations will diminish, right? And in other words, it will still be there, but the result will be better. So the average spectral efficiency for best response dynamics for the four-channel case will be better than the two-channel case. Okay, this is what you see here, actually, focusing on this oscillating curve here for the dashed red curve, right? So this is what you see. I mean, for the others, I mean, this is the best Nash. For example, if you focus on the regret matching here, again, it's a lower performance compared to the other best response dynamics here compared to the fictitious play. So just to summarize, I mean, for approaching the Nash, the best Nash, and if you make the assumption that you observe the actions taken by Colgatter agents, then of course this family of algorithm, namely best response dynamics, fictitious play, smoothed fictitious play will outperform the other ones. Okay, this is basically the